Okay, I've just started recording. I'm going to share the screen for you so that we can have a look at this first. Do you remember this? This is in the single dimension that we had the friction analogy. Do you remember that?
Yeah.
Is everybody able to see the screen?
Yes.
Okay. Now, I'll just go through all these ones and tell you how we now shift to a three-dimensional framework. Okay, and what are the difficulties and how do we tackle those difficulties? Okay. First of all, elastic range. Here we said if sigma is less than sigma y, it should be actually the absolute value of sigma is less than or equal to sigma y. No plastic flow. Correct? Right?
Yes, sir.
So that's the first one. Here, sigma is a single value. Once we have three dimensions, it becomes matrix. Sigma becomes a matrix. Correct? So, I can't assign sigma to be less than or equal to sigma y. I need to do something about that. Correct?
Yes, sir.
That's
Yes,
one thing that I have to fix. All right? The second one is yield condition. Yield condition is a condition at which the material may start to flow or is about to start flowing. Here also, we don't know what it is to say absolute value of sigma if sigma is a matrix.
Yes.
But if we are able to do something about that, then f is less than or equal to 0 is something that we can adopt for yield condition.
Yes, sir.
Let's go to the third one and then come back to all this again. Flow rule. What is flow rule? That the movement is always in the direction of the stress applied.
Stress applied.
Right? In this particular case, movement is nothing but plastic strain rate.
Yes, sir.
All right? And this has to be in the same direction as the stress. Now here also, stress is a matrix now. So if it is a matrix and plastic strain is also a matrix, how do I deal with that? That's the next question that we have to answer. All right?
Yes,
Now,
sir.
if we are able to answer that question, somehow I relate the flow, which is plastic strain rate, to the stress that is applied, then flow rule will help us understand what direction the strain rate is occurring. If you want me to repeat any of them, you have to tell me, okay?
Yes, sir.
Now, fourth one is a multiplier, that lambda. It just says that lambda is non-negative. I can keep it as it is. Keep it as it is. Because it just tells me the third one, flow rule, is such that lambda is a non-negative value. And then comes the last two conditions, which is when it has yielded and started to flow, then there is plastic strain rate. And when there is no plastic strain rate, there is elastic deformation.
It has not reached yield level.
Yes. Here also, if you remember correct, we said when the flow occurs, then the yield condition is met. That is, F is equal to 0. When the flow is not occurring, lambda is equal to 0. So the product of the two is equal to 0. The last condition, consistency condition, is derived from the previous one, where we say lambda times f dot is equal to 0. Since if lambda is equal to 0, then f dot sigma can be any value. If lambda is not equal to 0, then f dot sigma has to be equal to 0. What is f dot sigma? The change in the yield condition is equal to 0. Or in other words, the stress is always on the yield line. If you have doubt on any of these, you have to ask me now.
Sir, what was F dot sigma?
What sigma?
F dot sigma.
No, F is nothing but yield condition. Number 2. The change in the yield condition is equal to 0 means it is still in the flow. It is still flowing.
Okay.
With respect to change in time, it is still flowing. It is still plastic flow.
Okay.
Got it?
Yes, sir.
Okay.
Sir,
So we
for
use these in order to solve a one-dimensional problem. Now we want to solve a three-dimensional problem. Yeah, somebody else has a question?
yes, sir. Sir, for number 3, you said we'll have a matrix for both stress and strain.
Yes.
So, how do we know the direction of flow?
That's all. So
Yes, sir.
we need to fix all those. We need to fix all these in terms of 3 dimensions. How do we fix is the question that we will pose and try and answer. Okay?
So this
Sir, one
yield
doubt.
line.
Come again?
Yes, sir. So this yield line or
Yeah, right now it has 2 values. One the positive quadrant, the other is negative quadrant. That's all.
okay.
But once sigma becomes a matrix, how do I deal with that is the question. Okay?
Yes.
So let me go over to
Sir, these conditions hold for every time instant. Means
a time step
Why
comes about by the rate equations. All these are rates. This is a rate. This is also a rate.
why do we need that sixth condition? Is not
Fifth condition is just telling us that we have reached a point where it could start to yield.
no. So sixth one, consistency condition.
That is before and after what is happening. Supposing it was flowing, and if it
Okay.
continues to flow, then f dot has to be equal to 0.
Okay, sir.
That is all. It just gives us a feeling of whether the plastic flow is continuing to occur. Nothing more. Okay. This is something that you already did in your one-dimensional case.
So the consistency condition is just showing a continuity in flow, like, and as soon as that becomes non-zero, there's a break in continuity of flow.
Correct. So it is just saying continuity of flow. That is f dot sigma equal to 0. Loading condition is saying, okay, have I reached the yield limit or not? Am I in a plastic regime or not? But that's not enough for us. We need to say, oh, it is continuing to flow, or it has stopped continuing to flow.
Yes.
Whether it is
Yes,
stopped or not is something that we can find out through that. Okay?
Yes.
All right. Now, with this, let's move on to 3 dimensions and try and understand. Okay. Let me now go over to. So that's what is given in J2 plasticity. Okay. If you remember dash part, is my writing legible?
Yes, sir.
Yes, sir.
So dash part, we said that, can you help me out with this?
Sigma is equal to eta sigma.
We'll write in terms of
Epsilon
strain rate itself. Huh? We said epsilon dot
Is equal to
is equal to
sigma by
sigma
eta.
by mu.
mu.
Yes.
I'm going to write this as lambda times sigma, where lambda is equal to 1 by mu. Okay?
Okay.
All right? So this is what we wrote. If you notice this carefully, I have a sigma which is a stress quantity, and I have strain rate quantity.
Wait.
Correct? This is nothing but flow.
Yes, sir.
We related flow to the stress, and this is what we call as flow rule of the dashboard.
Hmm.
But we know for fluids, flow is primarily because of shear stress. Yes or no? And
Yes,
shear
sir.
strain. All right? Yeah?
Yes, sir.
Yes, sir.
Okay. Now let's look at this way. The strain rate that I have is nothing but plastic strain rate or viscoplastic strain rate. That is equal to lambda times sigma, where lambda is a value property of the fluid. Right? But in contrast, for dry friction, what did we state? In one dimension, what did we state? Help me out. Epsilon dot P is equal to lambda times correct?
Okay.
Yes, sir.
Yes, sir.
Now this is very deceiving because there is a rate term at the left, there is no rate term at the right.
Hmm.
You will feel odd. A nice way to do it is put a lambda dot over here. Okay.
But sir, why do we have why should both sides be a right term?
Yeah. So why should both sides be rate term? Is because in dry friction, the motion is time independent.
Yes, sir.
All right.
Yes, sir.
This lambda dot has the value, has the magnitude of motion, right?
Yes, sir.
Or in
Yes,
other
sir.
words, flow, magnitude of flow. The magnitude of this value, absolute value of this, is contained in this.
Yes, sir.
And whichever direction is contained in this. So this is direction, this is magnitude,
Okay, sir.
right?
Yes, sir.
But look at the similarity between these two. If you look at the similarity between these two, they look very similar, except that
Yes, sir.
I have this rate term coming into picture. It becomes a homogeneous equation.
The rate term means the lambda dot.
Right.
Like
Here it's a
my
constant value,
doubt was
but
okay.
here it is not a constant value.
So that's why we are keeping it as lambda dot.
Right. So this is a constant.
Okay, sir.
This is a constant reciprocal of viscosity.
Okay, sir.
Right. Here it is deceivingly inverse of viscosity, reciprocal of viscosity, but this is changing. You understood?
Okay, sir.
That's the primary difference between dry friction and fluids. All those questions that you asked earlier pertain to this difference. That this is a constant and this is a varying quantity. This can also be varying, but this variation will be different from the kind of variation that we are looking at here. This variation has to do with the flow magnitude. I don't want to confuse you now, but that's what it is. This is what we did in one dimension. This entire thing is one dimension, correct?
Yes, sir.
Yeah? Hello?
Yes,
Yes,
sir.
sir.
We are yet
Lagging
to
up.
we are yet to use this this fact that fluids flow due to shear stress and shear strain. Yeah?
Yes, sir.
Okay.
Now, this epsilon P, I'm going to retain it now, I'll tell you later, should be a function of not necessarily sigma, but the deviatoric component of sigma, ideally, correct? If you don't understand this, you have to ask me. What is deviatoric component of sigma?
Sigma minus the hydrostatic.
It is nothing but shear
Sigma minus
component.
sigma II over 3.
It is shear component
The
of
shear
sigma.
component.
Shear component.
Yes, sir.
Nothing but shear component of sigma. Okay. So this shear
So how
component,
did
I'm
that
going to
come,
write it as tau instead of sigma. I'll come to 3 dimensions and all those later.
So how did that part, like how did we come to know that it's deviatoric?
Because it depends on the shear stress primarily.
Oh, okay,
Flow depends on shear stress
for
only.
fluids. So
Yes.
it's specifically for fluids. Okay.
Yeah, in flow is pertaining to fluids. So for fluids, it is that way. I'm going to start off that way. Later on, we can add normal stress dependent flow. Okay. To start with, I'm starting with just shear stress. And therefore, I can write it like this. Okay. Now, in order to make it 3 dimension, all I need to do is I make this a matrix and I make this a matrix. All right. When I did this, I have actually invoked Navier-Stokes. Okay. Epsilon dot P is nothing but the velocity of the fluid. Okay.
So sigma is still a single valued function.
No. Supposing I change this to tau.
Okay.
And I also change this to a matrix. This wiggle means a matrix.
Yes, sir.
That is, this will have tau 11, tau 12, and so on. If it is 2 dimensions like this. Okay.
Professor, can you briefly tell what is Navier-Stokes?
Navier-Stokes is this, that the velocity depends on the shear stress that is applied. That is primarily what is now discussed. We can expand and write in terms of moving coordinate, etc., etc., Eulerian coordinate system, etc., etc. But basically, this is what Navier-Stokes used. Okay. All right. Is the silence an indication of I
No,
don't
sir.
understand?
We have
Yeah,
muted
our,
our.
so our net is lagging a bit, so we are trying to reduce
I see.
internet
Okay.
by muting.
Once you tell me I can move on, we will move on.
Yes, sir.
Yes.
Sir,
Yes, sir.
sir, for the component tau,
Hmm.
the diagonal components will be 0 or?
Yes,
There
It
I'll
will be
come to that.
zero. It will be
I'll
zero.
come to that.
Okay.
Shall I flip page?
Yes, sir.
Now,
Okay, sir.
That lambda dot
oh,
are we,
use,
why are we not using
come again.
lambda dot? We are not using in this matrix form.
No. This is
the
we'll come to
fluid.
that, but this is primarily for the dashboard.
Okay.
Oh, okay.
You'll invoke for dry friction again.
Okay.
Now, oops, sorry. What are you seeing right now?
Chapter 1.
The PPT.
Oops, sorry. I should use camera. Okay. Now, this is the important thing. Tau is shear stress, right? I'm just going to write the.
So we can't see. It's reflecting.
Light
much.
is, yes, sir. Now it's better.
Sorry.
Yeah.
Now, tau 11, tau 22. Tell me about the components here.
Tau 1 2, 12 to 1.
No.
Tau
It's
1, 2, tau 1. Yeah?
minus.
Yes, sir.
Okay. I'm just doing two dimensions so that it's easy for you. For a shear stress, the sum of diagonal terms is equal to 0. Or in other words, tau 11 plus tau 22 is equal to 0.
Is equal to 0.
Okay, sir. Yeah. Let's see 0.
Okay. So, what does that mean? Epsilon dot P is equal to lambda times tau. Lambda is just a multiplier.
Okay.
It's a multiplier scalar, correct?
Yes, sir.
Now, it is simple for me to adopt this fact, stating that epsilon dot P is such that the sum of diagonal terms should be equal to 0.
So,
Sum of. Are you able to read it?
Yeah. Yes, sir. Because
Yes, sir.
it will be scalar times the
Exactly.
diagonal terms anyway, so it has to be 0.
So if the sum of diagonal terms is equal to 0, it means what?
No change in volume.
No change in volume, or it is incompressible.
Incomplete.
So the equation that I wrote was Navier-Stokes for an incompressible fluid. So far, okay?
Yes, sir.
It's possible to extend to compressible fluid, but I'll tell you later. Now let's jump to dry friction. What is dry friction? plastic flow.
Yes.
What I'm going to do is I'm going to do the same thing again. I'm going to say epsilon dot P equals lambda times tau. Okay.
Lambda tau.
Lambda
So
dot,
shouldn't
right?
shouldn't it be a lambda dot now, sir?
Yeah. So this lambda is a rate quantity. The rate quantity. Let me see if it is easier for you to see it this way. I'm just going to make one alteration here. If I directly use camera, give me a second. It says can't start video. Okay, you're able to see me now. I'm just going to go to the other one.
No, sir.
Don't know why it's happening. Okay, I'll go back to the previous one. Okay. Sorry for the interruption. So you now notice this is a rate quantity. Okay. I'm just not writing it explicitly. That's all. When flow occurs,
So we can see you, but not the
Sorry,
screen.
screen. You have to share the screen.
thank you. Thank you.
Notes.
Yes, sir.
Yeah.
Yeah.
So when plastic flow occurs,
Yes, sir.
the direction of plastic flow is along the direction of shear stress. The direction of plastic flow is along the direction of shear stress. So far, okay?
Yes, sir.
Okay.
Yes, sir.
All right. Now, when will the plastic flow occur?
When the yield
When
starts
lambda
to
is non
negative,
Non-zero.
greater than
Non-negative.
equal to 0.
non-negative is correct and
And equal to
Greater.
0.
non-zero.
Non-zero.
Greater than.
So when lambda not equal to 0, epsilon dot P is equal to lambda times tau. This is the correct way of writing. Because I'm saying plastic, only during plastic flow, this is correct.
Okay.
What? So, shall I move on to the next page?
Yes.
So what about lambda equal to 0 condition? What shall we do?
And lambda is equal to zero. It's like we are on both.
Epsilon P dot is 0.
Only Pragyan,
Yeah.
Aditya, and Meher are participating. What about others? I need to hear from others. What about lambda equal to 0 condition?
Epsilon P dot is 0.
Epsilon dot p equals 0. Very good. Epsilon dot p equals 0. Who's that who spoke?
Utkarsh.
Pragyan, I guess.
No, sir.
Utkarsh.
I didn't say.
Yes.
Yeah, but I need to
Utkarsh, not
Utkarsh is
Yes, sir. I Utkarsh.
just relaxing.
Okay.
Kaushik probably is listening. Rajshekhar is not participating. Bhanu is just sleeping.
Oh, I
Yeah.
think my mother is also talking on the phone. I'll just close my door.
So interact now.
Guys, mute.
Lambda equal to 0 means epsilon dot p equal to 0. Yeah.
Yes,
Yes,
sir.
sir.
Anything else?
Epsilon P will be
It has not yielded yet.
It has not yielded yet. It has not yielded
Yet.
yet. Again, Aditya only was telling. Utkarsh,
Yes, yes, sir. Yes, not yet.
Utkarsh is not showing his face.
Okay.
You don't have to show your face, but interact.
Sorry.
Same with Chandana.
I muted so that I can avoid noise.
Okay.
Yes.
Now it has not
And-
yielded yet. How do I know whether it has yielded or not?
That's why.
If epsilon
When-
p is not
Yield condition.
So there
When
has
stress is less than
yield
yield.
condition. F of
Yield condition.
F
F
of
sigma.
sigma.
has
But
to
I already
Now-
know now whether I should be looking at sigma or tau.
we are looking at tau.
Tau
I have
now.
to look at
Right
tau.
now we are looking at tau.
Okay. Equal 0 is yield condition. Yield. So if it is less than or equal to 0,
Equal to
then it is a yield
yield
function.
Yield.
Yeah.
Yes, sir.
So what is this function? It was easy for me in terms of one dimension, where we said take tau value, take it to tau y, then it has yielded. I can take the absolute value of this, positive or negative. This was 1D.
Yes, sir.
But in 3 dimension, what shall I do? Okay. So one proposal is to take, listen to me carefully, take a particular measure of tau. It is also called norm of tau. I see silence now.
Yes, sir.
So what is
Sir,
the
any-
What is this particular measure? We'll discuss that.
Okay.
Now, what is it that we are dealing with? We are dealing with a material that is isotropic. Okay. We'll start with isotropic. We will move on to anything else later. Now, how do I now translate saying that the material is isotropic in terms of stress?
So the
Two material
Stress-
constants.
yield value is same in every direction?
Every
Fantastic.
direction.
yield value is the same in all directions.
All
Irrespective of,
directions.
so if I take something like this, if I take one coupon that is like this, or one coupon that is like this, and test it, it will give the same value, right? If it is isotropic. Yeah?
Yes, sir.
Now I need to introduce this. This needs to be introduced into this function. Then I am okay. Is
Sir,
it logically
the
works?
diagonals. So the oh no, not diagonals.
We can use the
Diagonals will anyways.
Sir, I have a question here.
Yeah.
Hello. Yes, sir. Sir, what I'm asking is, this we are assuming it as incompressible, right?
Yes.
So, like if we do some more circle analysis, we'll find some directions in which there are principal stresses, normal stresses.
Hmm.
Hello.
Yeah, yeah.
Yes, sir. So in that condition, it will not be valid, right? For
No.
incompressible.
You have
No way.
misunderstood. You have drawn more circle, right? You
Yes.
remember more circle. More circle has to do with stresses along various directions.
Yes, sir.
That is different from, supposing I take this or this, and let's say a stress is applied like this. What I
Yes.
will do is, I will take the component along this direction
Along
to
the
be
planes.
a load that is applied for that coupon, correct?
Yes, sir.
This is not what I'm talking about. I'm talking about if I take this material, apply tension like this. If I take this coupon and apply tension like this, I will get the same yield.
No, my question is regarding the matrix in which diagonal elements were 0. So I can find another matrix in some direction in which diagonal elements are not 0.
Yeah, it is
So
only
more
a stress
circles.
state, no?
Yes.
Doesn't matter what it is. The plane along which it will slide will be different. That's all. If you watched my other two videos that I uploaded through YouTube, it will be clear to you.
Tosca conditions.
Tosca condition. Have a look at that again.
Okay. Yes.
There are two things. One is about the material. The other is about the stress transformation.
Okay.
All right. Here what I'm saying is, if I apply the load in this direction or in this direction or any other direction, supposing I apply in this direction, take a coupon in that direction and apply, I will get the same
Yield
value.
stress.
That's what I'm talking.
Yes.
Okay. So how do I introduce this? That material is isotropic, and I want to introduce something like this, which is a measure. Any ideas?
Subtract sigma y in all the tau values and then check if it's greater than 0 or.
No. But it's a matrix, no? Sigma y is a single value.
Yeah,
Sir,
you
we
can subtract from
need
each.
like a von Mises
See,
stress
for
or
example,
something.
if I take something times tau y equal to 0, what is this something? That's the question we are asking.
So maximum stress or some von Mises stress, something like that.
Exactly. So we are looking at something where we translate it to a single value.
Yes.
And then comparing with this value. That's what we need to do.
Yes.
Right? The other thing is that it is isotropic means irrespective of the stress that is applied, it is not dependent on the direction that you find out. It is dependent on the invariance of the stress. What is an invariant of the stress?
There are 3 invariants are there.
If I have a matrix sigma 1 1, sigma 1 2, sigma 1 2, sigma 2 2.
So one is trace.
I want to find
So
out
they don't
invariance
change.
of this.
So trace is one invariant.
Eigenvalues of the matrix.
No,
One
no,
is
no.
trace,
One is the matrix.
Determinant.
Determinant, yeah. Determinant of
diagonal.
yeah,
Determinant of
exactly.
diagonal.
Determinant of sigma is the other.
and
Third
one is
Trace
trace
of
of sigma square minus trace of sigma whole square.
Whole
Or is
square.
it the other way?
And that is called the second invariant.
So
Second
that
invariant,
is
yeah.
Okay. In a simpler way, I can also say sigma 1 and sigma 2 are invariants. Two principal stresses. Irrespective of what I have written here, sigma 1 and sigma 2 are invariants. Correct?
Yes, sir.
Right? If I am able
Sir.
to write this,
Sir, sigma 1 and sigma 2 are only the eigen
principles.
values, right?
yes,
Yes,
eigenvalues
sir.
are invariant for a
Invariance.
matrix.
Matrix.
Of the stress. Irrespective of
Okay,
whichever
okay,
direction
okay.
you take, eigenvalues will remain the same.
Okay, sir.
Sir, only sum of eigenvalues will remain same, right?
No, eigenvalues will
No.
remain the same.
No,
They are the roots of the
Sorry,
characteristics.
sir. Okay, sir. Sorry.
Matrix.
Eigenvalues are always.
The eigenvalues
That
are
is
the
why-
roots of the
That is why it is named as invariant, right?
Clear now? Shall I repeat it once more?
Why are we looking for invariant, sir?
Why are we looking for an invariant? Because I'm looking at a material that is isotropic.
Okay.
And therefore, I have to make it independent of the directions.
Okay, sir.
Which means that the function that I take here, the measure that I take here should be a function of invariance of the stress.
Okay, sir.
Got it now?
Okay, sir. Got it.
Okay. I'll move on. One of those things that we did earlier in the Tresca is we wrote sigma 1 minus sigma 2 by 2.
Yes, sir.
Value of that. Maximum of sigma 2 minus sigma 3 by 2. Sigma 3 minus sigma 1 by 2. Minus tau y is equal to 0. This is due to Tresca. Do you remember this?
Yes, sir.
Yes,
I
sir.
want you to review this. Okay.
Okay, sir.
This will give you a single value. Another way of writing this is maximum of tau 1, 2. Don't mistake me for this. I'm going to put it as this is not tau 1, 2, which is a component. Okay. This is
Yes,
I'm
sir.
writing this as tau because it's the maximum shear in the 1, 2 plane. Tau 2, 3. I'll put it as max here so that it's clear to you. Tau 3, 1 max. Minus tau y equals to. This is what it is. Yeah?
Yeah.
Or in other words, what I'm saying is this is nothing but that function of tau, which is a single value, minus tau y equal to 0.
Sir, but maximum of that is not an invariant, right? Like, why are we?
Because I have
Why are
written
you
in
taking
terms of
max
invariance.
exactly?
I have written in terms of invariance here. Any function which is a function of invariance is an invariant, no?
So no, sir.
No, sir. I meant tau12, tau23, and tau31 are
Sigma 1
are they
minus sigma
related?
2. Yeah. This is,
They are directly related to the principal stresses. So
yeah,
difference
yeah.
of principal stresses will also
Exactly.
be invariant because principal stresses are invariant. Okay.
Exactly. Exactly.
Okay, sir.
And therefore, we got this kind of a thing, right?
Yes, sir.
But this is cumbersome.
Yeah, if you have many directions.
Just to write it as an absolute function of tau is tough. So what they did is they came up with a simple measure, which is nothing but inner product of the tau matrix. What is this? This is nothing but tau 11, tau 12, tau 12, tau 22 times tau 11, tau 12, tau 12, tau 22. This is what it means. Okay. Yes or no?
Yes, sir.
Yes, sir.
Is it so?
Yes, sir.
No, sir.
Is it so?
Transpose.
This is wrong.
Sir, it's inner product, right?
This is inner product.
Yes, sir.
Inner
Yes,
product
sir.
is nothing but tau 11 square plus tau 12,
Square by square root of
tau 12,
square root.
Shall I repeat this?
Raise
Square root of that, right?
Square root of that, sir.
No, tau, inner product tau is just this.
Oh, okay, okay.
Another way of writing this is tau ij,
IG.
summation over I, summation over j. 1 to 1 to 2
1 to
or 3.
1 to 2.
Yeah, if it is like this, 2 or 1 to 3. Okay.
Yes, sir.
This is nothing but tau inner product tau. For those who are not very familiar, this is what it means. Are you with me so far?
Yes,
Yes, sir.
yes, sir.
This we call as J2 because this is the second invariant of tau. Tau dot tau is the second invariant of tau. So far, okay.
Yes, sir.
Now
Yes,
I
sir.
can state that this function f of tau to be J2. So that now I can write root of J2 minus tau y equals 0 is the function of yield function of tau.
Yes.
Agreed?
Yes, sir.
One thing is that instead of writing, so initially we took f of tau as the maximum of sigma 1, tau 1 to tau 2, 3 and tau 3, 1.
Yeah.
Will the value be same as root of J2 or will this be a different value? or like this is
No,
a different.
this is a different one. I didn't want to go into this because this is a this can also be written as J2 and J3, by the way. Okay, what is J3? The third invariant. This is second invariant.
Determinant of the matrix.
First invariant of J2 is
Trace.
first invariant of tau is
0, 0.
Trace
zero.
of 0.
So
Trace.
it has only two invariants.
Sir,
Okay.
So
which
we are
is
reducing
more,
one invariant.
Yeah, I'm just taking one invariant
Well,
here.
So how does it translate? Sir? Like if you are reducing one invariant, does it affect the solution? Like we are getting some solution in some different
Mathematically, it
approach.
is simpler. It is mathematically simpler. That's all. So turns out that it is nothing but it is the average of these quantities: tau 1 2 max, tau 2 3 max, and tau 3 1 max. So turns out that it is the root mean square RMS of tau 1 2 max, tau 2 3 max, tau 3 1 max.
So
Sir,
J2
how
is
do we-
this.
If I take root of J2, it is the root mean square of these three values. These three values, 1, 2, 3. Yeah.
Sir, how do we the function can be some constant into that root of J2 also, right? How do we know that it is exactly root of J2?
Yeah, correct. It can be a constant also, but this constant I can borrow into this other direction and say tau bar y, no?
Okay. Yeah. Okay.
And therefore it doesn't matter if I don't put a constant over here.
Okay.
Understood? This one I can take,
But,
if you put a C over here, I'll take that
okay.
C and put it over here and say tau y by C. Just an equation, no?
Yeah, but then we have to determine that C somehow, right? To introduce this condition.
No, I'll just find out tau y by C instead of tau y.
Yeah, how do we find out the tau y by C?
Tau y by
Like
C,
not-
how do we find out? We'll come to. But right now,
Okay.
this is how it is. I don't have to put a constant here.
Okay, sir.
Shall I move on?
Yes, sir.
Sir, can it still not be that individual taus are lesser than the yield value and only the norm is greater than the yield value?
Yeah, correct. So here, in this particular case, I have just taken a sweeping value of root mean square of these three maximum. Here it is maximum of any three of these. If I take the root mean square, it will always be less than maximum of these three.
Okay.
Got it?
Okay.
Sir, in that maximum of tau 1 2 max, tau 2 3 max, what does that max mean? Tau 1 2 max, tau 2 3 max.
So if you go back to strength of materials, you will take 1 2 plane and find out the maximum shear there.
Yes, sir.
You will take the 2 3 plane, find the maximum shear there. You will take
Okay.
3 1 plane and find the maximum shear there. The maximum
More
of these
radius.
three shears should be the absolute maximum.
Okay, sir.
Sir, and J2 was preferred over J3 for any reason?
It is less cumbersome. J3 has the product of the eigenvalues. J2 is directly the square of the stress.
Components. Okay.
That is why. Another way of writing it, so you can write it as root of J2 minus tau y equal to 0, or J2 minus tau y square is equal to 0. Does not matter. Here it is, the dimension is square of the stress. Here the dimension is stress. That's all is the difference.
Okay.
So far, okay?
Okay, sir.
Okay.
Yes, sir.
So, how to find out tau y? So, let us say I have go ahead, somebody asked the question. I have something like this, all right?
Okay, sir.
This I can write as sigma is equal to, help me out,
Sigma 1
Sigma
1
1
0 0. Other all the terms are 0.
yeah? And what is tau here equal to?
Sigma
Here,
0 by 2.
here.
Yeah,
Sigma
Manu.
0 by 2.
It is sigma by 2. I mean,
Half of that stress.
Tau is
sigma
nothing
by
but
2.
sigma
But
naught
where
0 0 0 0 0 0 0 0 minus
Sigma II over 3.
Sigma naught by 3
hydrostatic
will
stress,
sigma
Okay.
naught by 3.
right? Which is sigma naught
Sigma
by
not by 3.
not by 3.
3.
3.
Not by 3 in the diagonals. Minus.
Is that okay?
Yes, sir.
Yes, sir.
This I'll get as 2 by 3 sigma naught
Sigma naught
0 0
0 0 0 minus sigma naught.
okay.
Yes, sir.
What is the sum of diagonals?
0.
0, sir.
0.
So it is indeed shear stress. That's a test I made. Why am I doing this, Banu?
Sir?
Check.
Why am I doing this? I'm adding these three and asking the question, is it equal to 0?
Yeah, because it is we have subtracted the hydrostatic component and the
Fine,
volume change.
but why am I testing by adding these three and checking whether it is equal to 0?
So, for checking if it is CR or not. There suppose not be any normal components are there, right?
Yeah. This,
J1 is 0.
yeah, this means that there is at least one orientation. There is at least one orientation in which normal stresses are 0. Only shear
0.
stresses occur.
No normal stresses should be there.
So it's a theorem that you can prove by yourself. For any stress that I have, if I take the component which is the shear stress component like this, and if I take this value, this matrix for any orientation, there is at least one orientation for which all the normal stresses will be 0.
Okay.
Sir,
Clear, Banu?
the hydrostatic matrix, we will compute it after we have decided the main matrix, the orientation in which we are calculating it, right?
Yeah, even otherwise it doesn't matter. You can always take any other direction and compute the hydrostatic component.
Oh, so it will be the same in
Yeah.
every.
So how do I do that? Let's say I have a stress here. Say sigma 1, sigma 1, 2, sigma 1, 3, sigma 2, 2, sigma 2, 3, sigma 3 3.
Okay, the trace is an invariant.
Correct.
Okay.
Yeah, invariant. So what I'll do is from this I'll find out sigma 1, sigma 2, sigma 3. Then the hydrostatic component P is equal to sigma 1 plus sigma 2 plus sigma 3 by 3.
By 3.
Because this is the invariant.
Mean
Invariant.
invariant.
It is also equal to the sum of these three.
Yes, sir.
Right? So I can find out this is nothing but sigma 1 1 plus sigma 2 2 plus sigma 3 3 by 3. So for this I can easily find out. And then I subtract sigma 1 1 plus sigma 2 2 plus sigma 3 3 by 3. 0 0 0. Same. This is P equal to. Okay. P 0 0. And if I do
after
this,
that, we have to check if it
I'll
is
get
pure shear or
for any stress matrix, it is possible for me to find out. Okay.
okay. Okay.
Okay, sir.
So what we have done so far is we have said, okay, this is the yield condition.
Professor,
Yeah.
for splitting the stress matrix into hydrostatic component and a shear component, you have done this.
Yes. Correct.
But
Diagonal and non-diagonal stress matrix.
Yeah, the pressure matrix or hydrostatic component matrix is a diagonal matrix consisting of sigma 1 plus sigma 2 plus sigma 3 by 3.
No,
Or in
instead
other
of
words,
finding the mean and subtracting, can we simply not write a given matrix as a sum of one diagonal matrix and sum of non-diagonal matrix?
you can, but the thing is, what are we trying to do? We are trying to separate the shear components alone. How do I define shear component? Shear component is one where it is possible for me to have at least one orientation where only pure shear stresses occur.
Yes, sir. So when you write as a sum of diagonal and non-diagonal matrix, the non-diagonal will have diagonal elements as 0.
Yeah, but it does not mean that you will get it to be only divitoric. It is not unique. This is unique.
Okay.
Is it Kaushik who is asking that question?
Yes, sir. Yes, sir. It's Kaushik, sir.
Kaushik.
Yes, sir. Yes,
Supposing I say, okay, let me write this as 0, sigma 1, 2, sigma 1, 3.
Yes, sir.
0, 0, sigma 2, 3.
Yes, sir. Yes, sir.
Symmetric. Right? Plus
sigma. Yes.
This.
Ah.
The thing is, this is not going to be unique. And this may not be unique.
Okay, varies with the direction. Yes, sir. The components will be.
Yeah. All right.
Okay.
Shall I move on?
Yes, sir.
So what we have done right now, I know it is too intensive. I'll stop it in a few minutes. What we have now done is we have written yield condition. Okay. So now I'm going to put them together. What is yield condition? Epsilon dot K equal to 0 when f of tau is less than 0. All right, implying tau dot tau dot tau. Go ahead.
Is equal to
minus
0.
K square. K square I have written here, but I can also write sigma y square.
Yeah.
What's the difference?
No difference. Both are yield
K-
stress only, no, sir.
No,
Yeah, it can be yield stress, but kappa is a more general way of writing it. In
Okay.
case I have hardening later, I can introduce that.
Sir, and K is a variable, right?
K can be a variable. It can also be sigma y.
Okay.
In
Yeah,
this particular
K can
case,
be-
kappa is equal to sigma y. Sorry, tau y. I'm consciously writing tau here so that we keep remembering that it is the shear that we are looking at. So far, okay?
Yes,
I
sir.
have one question, sir.
Epsilon dot p is not equal to 0.
Sir, we switched sigma to kappa. Sigma to tau. When we switched from 1D to 3D. So, but when we go back to 1D, it still becomes sigma, right?
Yeah, so we have not done that yet, no?
Why did we
Let's do
switch
that.
to tau when we go to?
Because in uniaxial case, it did not matter much. The single value.
Yes, sir.
Here it is not a single value. Shear and normal stress matter.
So the normal stress component doesn't come into the picture during plastic deformation. Is it the conclusion or?
Yes,
Okay.
that plastic flow is incompressible in most metals.
Okay.
When we introduce compressible flow, we will discuss that.
Okay.
Oh, okay.
Coming back to this,
Okay.
we have not yet done this. Can you compute what is J2 equal to? Which is tau dot tau. It will be equal to 2 by 3 sigma naught square
Not
plus minus sigma naught by 3
whole square.
plus minus sigma naught by 3 square.
The whole
Correct?
Yes, sir.
Yes, sir.
So this comes out to be
4 by 3
by
sigma naught.
3.
Oh,
2 by
no,
3
not
sigma
2 by.
naught.
That's
2 by
by
3.
8.
2 by 3.
2 by 3 to 4. 6.
4 by 9
2 sigma naught square. 2
by
sigma naught square.
plus 1 by 9 plus 2 by 3.
2 sigma naught square.
4, 5,
2
6.
by 3, sir. 2 by 3.
6 by 9.
2 by 3 sigma naught square.
Okay, that's 2 by 3. All right.
okay.
Yes,
Now
sir.
sigma naught is the yield here. When this goes to yield, this goes to sigma y. Correct?
Yes, sir.
Yes, sir.
I take it over here and say, shall I
2
write it
by
here?
3. Yes, sir.
So it
2 by
J2 minus
Minus tau
y square.
2 by 3 sigma naught equal to 0.
एक second.
and
Sir,
this
it shouldn't be 3 by 2.
Ah,
It should go the other way around.
sorry.
Why did it
yeah,
become 2 by 3?
because J2 only have written it as 2 by 3.
Yeah.
Yeah.
It's changing it. Sorry, it's changing.
What should I write here?
3 by 2, sir.
3 by 2. It should be 3 by 2, sir.
Why
Because
3 by 2?
J2 is 2 by 3.
Very good.
J2 is 2 by 3, so it changes sign.
Very good. So
And shouldn't it be tau was y,
This
sir,
kappa
not
square.
sigma y?
Come again?
Yes, sir.
No, this is sigma y.
Sir, that should be 2 by 3, sir.
2 by 3 only.
Yes, sir.
Yes,
2 by
sir.
3.
No, sir.
No. It's 3 by 2 only.
No, it is 2 by
No.
3.
1 second.
1
Oh,
minute, sir.
sir. Okay, wait. Sir, you have written it as J2, sir. You have not written it as sigma naught.
Sigma naught square.
Huh.
Sigma naught square minus 3 by 2 sigma y
Minus-
square equal to 0.
minus 2 by 3.
What should come over here?
I think it should be just 1 because it's just the
It is
formula,
one,
right?
that's
J2
all
minus
one.
sigma
Yeah,
y.
yeah.
Yeah, it's just 1. It's just 1.
Yeah,
Yeah, sir.
When
It
we
would be 1
substitute for J2, then that 2 by 3 and 3 by 2 should come. When we substitute for J2. Yeah. For now, it's just 1.
Yes, sir. Yes, sir.
No.
But we have
The
way to
J2
calculate
is
tau.
this,
2 by 3,
okay?
sir.
Which is nothing but 2 by 3 sigma y square.
Yes, sir.
Exactly.
For this case alone, it is 2 by 3 sigma y square. So 2 by 3 sigma y square minus tau y square is equal to 0. Correct?
Yes, sir.
Right? And therefore tau y square is equal to
Yes, sir.
2 by 3 sigma y square. Okay, okay. Okay, we got
Yes, sir.
confused between sigma and tau.
That should be the case.
what
Yes,
should I write now?
2 by 3 sigma y square.
2 by
Right, sir.
yes, sir. J2 minus 2 by 3 sigma y square.
Okay. And that is nothing but kappa square. Is it clear now?
Okay. Yes, sir.
Yes, sir.
Yes. Yes, sir.
So is this tau y? If I have to write it in terms of uniaxial tension, this will be nothing but root of 2 by 3 sigma y.
Sigma y.
Correct?
Yes, sir.
And epsilon dot p is not equal to 0 when f of tau is equal to 0 when
Yes, sir.
when epsilon dot p is not equal to 0,
0, f of tau is 0.
then f of tau is equal to 0.
Yeah.
We had one more condition. What was that? Epsilon dot p is also equal to lambda
0. Okay.
Lambda dot into f of t.
lambda tau.
Lambda dot e. Tau.
Correct?
Yeah. Yes, sir.
So this holds good. This I have done. This I have done. In essence, I have all these available for me to write the rigid plastic constitutive equation. Let me see if I can pull that out. So if you look at this, the variables are tau. Take this as epsilon dot ij. Okay, write this as epsilon dot ij. In my book, I have followed this all the time. Deformation gradient. Okay. D is the symmetric part of deformation gradient for those who have done continuum mechanics. Yield function we have already stated. Elasticity response, the body is rigid. Okay. What are we looking at? J2 rigid plastic model. Flow rule, epsilon dot p is equal to lambda times tau. This is lambda. Kuhn-Tucker condition, lambda f is equal to 0. Value of lambda is such that it is epsilon dot p value divided by kappa. This is just possible to derive directly from whatever you have written earlier.
Okay.
Okay.
Lambda should be. Okay.
These examples, don't worry about it right now. You can just move on. If you understand, fine. If you don't understand, don't worry about it. Yes, Chandra. Chandra has gone back to sleep.
No, sir, I'm listening.
She's there. Okay. In the next class, what we will do is we'll focus on how do I introduce elasticity.
Okay.
So, if you remember, this is nothing but dealing with only this.
Yes, sir.
Now we want to add this also.
Spring.
Okay. This
Okay, sir.
is rigid plastic, and this entire thing is J2
Elastoplastic.
elastoplastic. Got it?
Yes, sir.
Yes, sir.
So what we will do is we'll do J2 elastoplastic and see what kind of equations we get. Then we will move on to how to add hardening to it, because there also I have to now shift to 3 dimensions. After we finish that, let's see how we can compute. Okay. How we
Sir,
can
this
compute. Yeah, Subhash. Go ahead,
sir,
Subha.
that friction block we can also replace with a damper dashboard, no sir?
Yeah, see, this is elastoplastic model. If it is,
Yeah, that can be combination of dashpot and spring as well.
yeah, if you put it as dashpot and spring, it will be viscoelastic.
Okay.
Not elastoplastic.
Okay, okay, that will be
We are not
viscoelastic.
looking at that right now, because viscoelastic, you can do always that also. Which is more difficult is what I am now dealing with. You can try viscoelastic once you are able to understand elastoplastic.
Okay, sir.
Because elastoplastic is more difficult to understand.
Sir.
You can always have same kind of combination. Supposing you want to put, let's say, a dashpot over here, and all those combinations are possible in 3 dimensions also.
Okay.
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 Yes, sir.
Now, any questions you can ask me now, or you can send me by WhatsApp. Okay.
Yes, sir.
It is involved. I want you to go through the video again, get an understanding.
Yes, sir.
Okay.
Okay, sir.
The coming classes are going to be a little tough, so I want you to keep reviewing what you have understood. Okay.
Okay, sir.
Sure.
Okay. Thank you.
Thank you,
Okay,
sir.
sir. Thank you, sir.
Good night.
Thank you. Bye.
Yes, sir. Good night.
Good night.
Okay, thank you, sir.
I'm ending the meeting.
Yes, sir. Sure.
Sure.